The expansion valve, precision flow control in refrigeration. Today, we focus on perhaps the most underestimated yet critically important component in refrigeration systems, the expansion valve. This small but sophisticated device controls the flow of refrigerant and creates the pressure drop that enables the entire cooling process. Despite its modest size, the expansion valve's precision operation determines system efficiency, capacity, and reliability. Historical development of flow control. The need for refrigerant flow control became apparent in the earliest vapor compression systems. In 1834, Jacob Perkins' original patent included a crude expansion device, though it was little more than a simple orifice. The real challenge emerged as systems became more sophisticated and engineers realized that refrigerant flow must be precisely matched to varying cooling loads. The late 1800s saw the development of hand-operated expansion valves, requiring skilled operators to manually adjust refrigerant flow based on system conditions. These early valves were essentially needle valves that operators would open or close based on sight glass observations and pressure gauge readings. This manual operation was labor-intensive and prone to human error. But it established the fundamental principle that refrigerant flow control is critical to system performance. The breakthrough came in 1922 when the first automatic expansion valve was developed. This pressure-actuated device could automatically adjust refrigerant flow based on evaporator pressure, eliminating the need for constant manual adjustment. However, these valves couldn't respond to changing load conditions effectively, leading to inefficient operation under varying demands. The thermostatic expansion valve emerged in the 1930s as the solution to variable load control. This ingenious device sensed both evaporator temperature and pressure, automatically adjusting refrigerant flow to maintain optimal evaporator superheat. The TXV represented a major advancement in automatic control, enabling refrigeration systems to operate efficiently across wide variations in cooling demand. Modern electronic expansion valves appeared in the 1980s, incorporating microprocessor control and stepper motor actuation. These devices provided unprecedented precision and could be integrated into sophisticated system controls, marking the beginning of truly intelligent refrigeration system operation. The mechanism of expansion and control. The expansion valve performs two critical functions. Simultaneously, it creates a pressure drop that enables the refrigeration cycle. It controls refrigerant flow rate to match system demand. Understanding this dual function reveals why proper expansion valve operation is so crucial to system performance. The pressure drop function occurs as high-pressure liquid refrigerant passes through the valve's restriction. This sudden expansion causes the refrigerant's pressure and temperature to drop dramatically, often from over 300 CIs to less than 50 psi in typical systems. This pressure reduction is what enables the refrigerant to evaporate at low temperatures in the evaporator. The flow control function is more sophisticated and varies significantly between valve types. The valve must meter exactly the right amount of refrigerant to match the evaporator's heat absorption capacity. Too little refrigerant flow results in starved evaporator operation with excessive superheat and reduced capacity. Too much refrigerant flow causes liquid refrigerant to return to the compressor, potentially causing damage and reducing efficiency. The expansion process itself is nearly isenthalpic, meaning it occurs at constant enthalpic. While pressure and temperature drop dramatically, the refrigerant's total energy content remains essentially unchanged. This thermodynamic principle is crucial because it means the expansion valve doesn't remove energy from the system, simply changes the refrigerant S state to enable heat absorption in the evaporator. Types of expansion valves. From simple to sophisticated, manual expansion valves remain useful for systems with constant loads and skilled operators. These simple needle valves allow precise flow adjustment but require manual operation. They're still used in some industrial applications where load conditions are predictable and operator expertise is available. Automatic expansion valves maintain constant evaporator pressure regardless of load variations. These pressure-actuated devices use a diaphragm or bellows that responds to evaporator pressure to modulate valve opening. While simple and reliable, AXVs can't optimize system performance under varying loads, because they don't account for evaporator superheat. Thermostatic expansion valves represent the most common expansion device in commercial refrigeration. These ingenious devices use a sensing bulb filled with refrigerant that responds to evaporator outlet temperature. The bulb pressure works against evaporator pressure and spring pressure to control valve opening. This arrangement automatically maintains proper superheat, ensuring efficient evaporator operation while preventing liquid refrigerant return to the compressor. TXVs come in various configurations, internally equalized for short evaporators with minimal pressure drop, externally equalized for longer evaporators with significant pressure drop, and balanced port designs that maintain stable operation across wide pressure ranges. Distributor-equipped TXVs ensure even refrigerant distribution in multi-circuit evaporators. Electronic expansion valves provide the ultimate in precision control. These devices use stepper motors to position the valve opening with exceptional accuracy, typically controlled by microprocessors that can consider multiple system parameters. EXVs can maintain superheat within 1 to 2 degrees Fahrenheit compared to 5 to 10 degrees for mechanical TXVs. They also enable advanced control strategies like capacity modulation and system optimization algorithms. Capillary tubes, while not valves in the traditional sense, serve as expansion devices in many residential systems. These long, small-diameter tubes create pressure drop through friction rather than a variable orifice. Capillary tubes are simple, reliable, and inexpensive, but they can adjust to varying load conditions. They're carefully sized during system design to provide proper refrigerant flow at design conditions. These simple devices work well in systems with predictable load patterns and are often used in residential heat pumps and some commercial applications where cost is a primary concern. Advanced control technologies. Modern expansion valve technology incorporates sophisticated control strategies that optimize system performance beyond simple superheat control. Adaptive control algorithms learn system behavior and adjust control parameters automatically. Some EXVs can control multiple parameters simultaneously: superheat, capacity, and even oil return to compressors. Intelligent expansion valves communicate with system controllers via digital networks, providing feedback on valve position, superheat, and flow rates. This information enables system-wide optimization strategies that consider expansion valve operation in context with all other system components. Variable geometry expansion valves can adjust not just opening area, but also flow characteristics, optimizing performance across extreme operating ranges. Conclusion. The expansion valve exemplifies how small components can have enormous impact on system performance. From the manual valves of early refrigeration systems to today's microprocessor-controlled electronic devices, expansion valve technology continues advancing to meet demands for improved efficiency, reliability, and control precision. Whether it's the simple capillary tube in your home refrigerator, the thermostatic expansion valve in your air conditioner, or the sophisticated electronic expansion valve in a modern supermarket display case, these devices quietly perform their critical function of controlling refrigerant flow and enabling the refrigeration process that enhances our daily lives.